Hi y'all, this is 1-3 square roots. The side length of a square is the square root of its area. This relationship is shown by a radical symbol. And the number or expression underneath that radical symbol is called the radicand. So for example, if we're looking down here, we have our radical symbol, and then that 25 would be our radicand. The radical symbol indicates only the positive square root, which we call the principal root. Okay, if we would like to indicate both the positive and negative square roots, we need to use our plus or minus sign. Or if we would like a negative number to come out, we need to include a negative in front of our radical symbol. Okay, it says the side length of a square is the square root of its area, right? So if we have an area of 25 in our square, we would know that the side length is 5. This indicates that the square root of 25 is 5. All right, numbers such as 25 that have integer square roots are called perfect squares. Square roots of integers that are not perfect squares are irrational numbers. Okay, I want to pause there before we move on. We're actually going to skip down to this table below. I'd like to fill out some perfect squares. This is going to be helpful to reference in the rest of this video and in class when we practice. Okay, so we know that 1 squared is the same as 1 times 1, which we know to be 1. Because that's true, we know then that the square root of 1 is 1. 2 squared is the same as 2 times 2, which we know to be 4. Therefore, the square root of 4 is 2. 3 squared is 9, so the square root of 9 is 3. 4 squared is 16, so the square root of 16 is 4. Okay, I'm going to cut the video real quick. I'm going to fill out the table, and then I'll hop back and show it to y'all so you guys can fill it out. Okay, I had to zoom out a little bit so y'all could see the whole table, but I would pause the video right now so you guys can fill this all out. Right, jumping back up here, square roots of integers that are not perfect squares are going to be irrational numbers. We can estimate the value of these square roots by comparing them to the perfect squares that we know. So for example, the square root of 5 is not a perfect square, but we know that that 5 is in between 4 and 9, right? And the square root of 4 and the square root of 9 are perfect squares. Because the square root of 4 equals 2 and the square root of 9 equals 3, that means that the square root of 5 is going to lie between 2 and 3. Okay, let's practice this concept. So number 1 asks us to estimate the square root of 34 to the nearest tenth. So using your chart if you need to, we need to find a perfect square that has a radicand that is less than 34 and a radicand that is greater than 34. In this case, we know then that 34 is in between 25 and 36. Okay, using our chart if we need to, we know that the square root of 25 is 5 and the square root of 36 is 6. So now we know that the square root of 34 is in between 5 and 6. If we're looking at our original radicands here, I know that 34 is closer to 36 than it is to 25. What that means then is the square root of 34 is going to be closer to 6 than it is to 5. So I'm going to test a bunch of different options in my calculator, okay? So I'm going to start with 5.6 squared, right? Because we know it's got to be closer to 6 than it is to 5. So it has to be greater than 5.5. And we're going to test all of these guys. All right, so using your calculator, 5.6 squared should get us about 31.36. 5.7 squared should be 32.49. 38 squared is 33.64. And 5.9 squared is 34.81-ish. Okay, looking at all of our values that came out, we'd like to figure out which one is closest to that 34 that we want. In this case, it's going to be 5.8 squared gets us that 33.64. Therefore, we're going to write that the square root of 34 is approximately 5.8. Okay, that little squiggle equal sign means approximately. Okay, we're going to discuss some properties of square roots now. So the product property of square roots states that the square root of a product is equal to the products of the square roots of the factors. So what that means, if we have the square root of 12, I know that 12 is the same as 4 times 3, so I can replace that 12 or that radicand with 4 times 3. Once I have a product as my radicand, I can split that into two separate radicals. Then, because I know that the square root of 4 is a perfect square that gets me 2, I can replace that, and my final answer, or the equivalent of the square root of 12, is going to be 2 square root of 3. That also works the opposite way. So if I have two radicals that are being multiplied, I can combine the radical to be the product. And in this case, 8 times 2 gets me the square root of 16, which is 4. Okay, the quotient property of square roots is pretty similar. It says the square roots of a quotient is equal to the quotient of the square roots of the dividend and the divisor. So if I have the square root of a fraction, I can split that square root up to apply to the top and the bottom, or the numerator and the denominator. In this case, we know the square root of 25 is 5 and the square root of 16 is 4. So the square root of 25 over 16 is going to equal 5 over 4. Okay, again, it works the opposite way. If I have two radicals that I'm dividing, I can add the radical symbol to the entire fraction. In this case, 18 divided by 2 is 9, and we know that the square root of 9 is 3. Okay. Notice that these properties can be used to combine quantities under the radical symbol or separate them, right? We can go both ways. Either way, this is helpful for simplifying square root expressions. And a square root expression is in simplest form when these two conditions are met. First, the radicand has no perfect square factors other than 1, and there are no radicals in the denominator. Okay, recall that the denominator is the bottom of the fraction. Okay, and if these two conditions are met, then a radical is said to be in simple radical form. Okay, let's practice using these properties to simplify an expression. So if we have the negative square root of 50, we would like to simplify this as much as possible. What we're going to do is start by figuring out if there are any perfect square factors of 50. If we look at our chart, if we need to, we know that 25 is a perfect square. We also know that 50 is the same as 25 times 2. Okay, so I'm going to rewrite this. Instead of negative square root of 50, I'm going to have negative square root of 25 times 2. Now that we have a product in our radicand, we can separate our radicals. So I'm going to have negative square root of 25 times the square root of 2. We did this because 25 is a perfect square, so we can simplify this to be negative 5 square root of 2. Okay, let's take a look at part B. We're going to use the quotient property here. We have a radical over an entire fraction, so I am going to divvy this up so that it can apply to the numerator and the denominator separately. Okay, we're in luck here because 49 and 81 are both perfect squares. Okay, my screen jumped, so it might have freaked out a little bit, but we know that the square root of 49 is 7 and the square root of 81 is 9, so the square root of 49 over 81 is going to be 7 over 9. If a fraction has a denominator that is a square root, we can simplify it by doing what we call rationalizing the denominator, or getting rid of that square root in the denominator. To do this, we multiply both the numerator and denominator by a number that produces a perfect square under the radical sign in the denominator. Okay, we are going to use our product property here to do that. Okay, so remember that if we have two radicals being multiplied together, we can combine those into a single radical. So what I need to do is, in this example, I have 2 square root of 2 divided by the square root of 3. I would like to make this square root of 3 into a perfect square. I know that 3 times 3 is 9 and that 9 is a perfect square. So what I'm going to do is I'm going to multiply the numerator and the denominator by the square root of 3. 3. Okay, writing out all my steps. In my numerator now, I have 2 times the square root of 2 times the square root of 3. And in my denominator, I have square root of 3 times the square root of 3. Using that product rule, I can combine those radicals. So I'm going to have 2 times the square root of 2 times 3 divided by the square root of 3 times 3. Okay, that gets me 2 square root of 6 over the square root of 9. And we know that the square root of 9 is 3. So our final answer is going to be 2 square root of 6 over 3. All right, let's take a look at part B. First thing we want to do is use our quotient rule to divvy this up into the square root of 8 over the square root of 18. Okay, we want to rationalize our denominator now. So if we're thinking of all of our multiples of 18, what can we multiply 18 by that's going to get us a perfect square? I know that 18 times 2 is 36, so I'm going to multiply both the numerator and the denominator by the square root of 2. Okay, I'm going to have the square root of 8 times the square root of 2 over the square root of 18 times the square root of 2. If I combine my radicals now using my product rule, I'm going to have the square root of 8 times 2 over the square root of 18 times 2. 8 times 2 is 16, so we have the square root of 16 over 18 times 2, which we said is 36. We got lucky here. Both the square root of 16 and the square root of 36 are perfect squares. So I'm going to have 4 over 6, which is the same as 2 over 3. All right, square roots that have the same radicand are called like radical terms. We're looking at some examples here. The square root of 2 and 3 square root of 2 both have that square root of 2 component. Negative 6 square root of 15 and 7 square root of 15 both have that square root of 15 component. To add or subtract square roots, first we have to simplify so that each radical term is in simple radical form, and then combine like radical terms by adding or subtracting their coefficients. For me, I want to explain this real quick. The easiest way to think about adding or subtracting radicals is to think about adding or subtracting variables. So if I were to have something like 5x plus 2x, I'm going to add my coefficients 5 and 2 to get 7, and that x is kind of just plopped onto the end there. It is the same thing with radicals. Let's take a look at part A, and that'll make a little bit more sense. We have 5 square root of 2 plus 3 square root of 2. I'm going to add my 5 and my 3. I'm going to add my coefficients to get 8. And I'm going to plop that square root of 2 right on the end. Okay, B is a little bit more complicated because that square root of 12 is not in simple radical form. We're going to use our product property. So I'm going to leave 5 square root of 3 alone. And I'm going to rewrite 12 as 4 times 3. Okay. Again, 5 square root of 3 gets left alone. Because we have a product as a radicand now, I can split up those radicals. And we know that the square root of 4 is 2, and the square root of 3 is irrational, so we're going to leave it just like that. Again, just as if we were dealing with variables, we're going to deal with our coefficients first. So 5 minus 2 is 3, and the square root of 3 gets plopped on at the end. All right, that was the video for today. So get ready to practice this in class. Bye, y'all.